The following program is brought to you by Caltech.
Today we have basically all over the world a vast number, an astounding number of highly capable computing devices made out of semiconductor chips that are all linked together. And that network of interconnected computing devices touches the lives of almost every human being on the planet. It's by far the biggest change of any kind that has ever happened to humankind. In aggregate, that's a big thing. Did we have any part in that? My first experience with electronics was with vacuum tubes. And when I was a high school kid, I read about this transistor thing the Bell guys had invented. What I didn't realize was Caltech alumnus Bill Shockley had basically out of whole cloth invented the semiconductor physics viewpoint and way of looking at things and some of the devices that came along. And that's what we've been living on ever since. Absolutely fundamental to everything we do. Wasn't seen that way at the time, but that's what it turned out to be. Then, of course, as Jean-Luc pointed out, Caltech alumnus Gordon Moore has probably done more than any other single human being to take that basic technology and bring it to the world. It was interesting when Gordon first observed that the economics of semiconductor manufacture drove you to put more capability per device. Now, of course, there was a small hurdle to get over, and that is how do you make devices on the same piece of silicon so that you can make a circuit out of them? They aren't all just shorted together by the substrate. That was Bob Noyce's invention of the integrated circuit. Once they had figured that out, then it was very clear if you made more of them and you could hook them up, there was more value per item that you had to manufacture. And that was the beginning of what came to be later called Moore's Law. You would have thought that once Gordon had said that, which he did in 1965, in a nice little article, which many of you have seen, you would have thought it would have just been obvious to everyone. Wrong. Because there were a whole bunch of papers out there that said the transistors are already getting so small that this or that or the other catastrophe is about to overcome us, and they won't work if you make them any smaller or crowd them together anymore. And there were at least 20 reasons advanced why you couldn't go beyond the scale at which transistors were manufactured at the day. So it was common lore that you just couldn't do that. So it was left to people on the campus to go back and figure out the physics behind these things and figure out how small you could really make these things. And it turned out that after some people looked carefully at that there really wasn't anything that was going to get difficult until it got to be like 1/10 of a micron. In those days, they were 10 microns. So that was a factor of 100 in size, a factor of 10 to the 4th in density. Well, you may imagine that there was a fair bit of hornet's nest stirred up over observations like that, especially when it was pointed out that if you scaled the devices smaller and you scaled down the voltages and other dimensions in the right way, that everything got better. The devices got faster. The power density didn't change. So a given size chip would continue to dissipate a given amount of power per unit area. And everything got better. That was, of course, you know that Murphy never goes on vacation, but he did. So that was a violation of Murphy's Law. That was amazing. That was a hard sell. And in the process of all this, Caltech took a very active role in not just the physics of the devices, but also in how you design them. What do you do to design something with 1 million working parts? That had never been done before. So how would you go about that? Things like if you're going to be making devices like this, they're going to be complex. They're going to do a lot of computing. They're going to be everywhere. So they have to be connected. So the prognosis was made right here on campus that the communication industry and the computation industry weren't going to be separate. This was going to be one big technology. That was, many of you remember, during the days when there was a consent decree from the Supreme Court that said that computation and communication would forever be separate. And if you did one, you were not allowed to do the other. Well, if we look out in the world today, that's not how it is. The other observations that were made right here on campus were that, the set of talents that it takes to manufacture semiconductor devices, incredibly precise and exacting chemical process. And the talents it takes to do that are really different from the talent it takes to understand a large computation and communication system. So sooner or later, they'd be done by different groups of people. That was not a popular comment in the semiconductor industry. And it has ended up now that what's now called the fabless semiconductor model of doing business accounts for roughly half the value that's created in semiconductors today. So there was a whole lot more going on than just technology. It was about how it fits in society, how it fits in business, and that sort of thing. So enough's been said about integrated circuits and computation. I think we heard a lot about it today, a lot of wonderful, wonderful things going on. But what about the communication side? Well, in today's world, as you all know, communication is done by laser beams going over fiber optic for a backbone, and then RF radio links with sophisticated encoding of digital data for the last spread at the end. So did Caltech have anything to do with that? Well, actually, yes. Caltech alumnus Charlie Towns proposed the first stimulated emission device, demonstrated that, wrote the book that analyzed that you can make masers and lasers. And when he was proposing this, he went to both Bohr and Heisenberg. And they both said, in effect, Sonny, you just don't seem to understand how quantum mechanics works. Amnon and I were having dinner a while back, and we were talking about this, and Amnon said, yes, and we never bought it. the whole statistical garbage about quantum mechanics just isn't physics, that's all. So we never bought it. And Charlie didn't buy it. So he went ahead and made the first maser. But even the early lasers aren't really suited for a communication system like we have today. They don't really fit nicely in a fiber optic environment. The lasers we use are semiconductor lasers. Well, where'd that come from? Well, the first semiconductor laser, as you heard from Amnon today, was built by Caltech alumnus Bob Hall at the GE Research Lab. And of course, immediately afterwards, everybody jumped in and did that. But Bob, Caltech alumnus, did it first. Bob has been under-recognized for that achievement, for I think largely political reasons. Of course, those early semiconductor lasers weren't nearly good enough, and so it fell to Caltech faculty member Amnon Yarev to invent the distributed feedback laser that he told you about today, which was actually up to the job. And that's what we have. 3 Caltech people in series it took to do that one. So it must have been tougher than the integrated circuit stuff. Well, but what about the end? We have sophisticated digital codes on RF links. Did Caltech have anything to do with that? Well, as a matter of fact, yes. I think you would all agree that the effort that really hatched the fundamentals under our communication technology of today started in Caltech's very own JPL Deep Space Network. A bunch of incredibly talented people that basically, out of whole cloth, came up with what's recognizable as the precursor to our modern art form. That's pretty amazing. We're very fortunate that because we're so close to that effort, it lives on in EE today, and that's wonderful. So here's the biggest thing that's ever happened in the human race. And here's a little tiny institution that when you go and look at the really fundamental shifts in thinking that led to this thing we call the information revolution, Caltech is front and center in every aspect of that. So why is that? What was there about Royal Sorensen's blunder that led to this Caltech being there when there's these big paradigm shifts? Well, I propose that the biggest gift that Royal Sorensen gave to Caltech is he had a different view of engineering than other schools did. Engineering wasn't something you studied and learned and memorized and knew where to look up. Engineering was understanding things all the way to the bottom, no matter what field they were called, and being able to use that to build stuff and make it work.